Welcome to Part 2 of the API 510 Exam Calculation Masterclass. In this part, we will focus on internal pressure calculations and maximum allowable working pressure, commonly called MAWP. We will examine cylindrical shells, spherical shells, ellipsoidal heads, and hemispherical heads. We will also briefly discuss external pressure and explain what the API 510 examination expects you to understand about it. Let us begin with internal pressure. And UG-27, paragraph C, item 1, for cylindrical shells. UG-27, paragraph C, covers cylindrical shells. The ASME code states, the minimum thickness or maximum allowable working pressure of cylindrical shells shall be the greater thickness or lesser pressure as given by item 1 or item 2. For the API 510 examination, the body of knowledge specifically requires UG-27, paragraph C, item 1. This is the circumferential stress equation associated with longitudinal joints. The code states, when the thickness does not exceed 1/2 of the inside radius, or P does not exceed 0.385 SE, the following formula shall apply. The equation is T equals P multiplied by R divided by S multiplied by E minus 0.6 P. In this equation, T is the minimum required thickness in millimeters. P is the internal pressure in megapascals. R is the inside radius in millimeters. S is the maximum allowable stress in megapascals. E is the joint efficiency. What does this requirement mean? For most API 510 examination problems involving cylindrical shells, internal pressure is acting on the shell. The internal pressure creates circumferential stress, which is also called hoop stress. This stress normally controls the pressure design of a cylindrical shell. The shell thickness is therefore calculated using the UG-27, paragraph C, item 1 equation. Consider example 1, calculating the required thickness of a cylindrical shell. The given internal pressure, P, is 2.0 megapascals. The inside radius, R, is 1,000 millimeters. The allowable stress, S, is 138 megapascals. The joint efficiency, E, is 1.0. We begin with the equation T equals PR divided by SE minus 0.6 P. Substituting the values, T equals 2.0 multiplied by 1,000 divided by 138 multiplied by 1.0 minus 0.6 multiplied by 2.0. The numerator is 2,000. The denominator is 136.8. Therefore, the required thickness is 14.62 millimeters. Now consider example 2, the effect of a reduced joint efficiency. The internal pressure, P, is 2.5 megapascals. The inside radius, R, is 1,200 millimeters. The allowable stress, S, is 138 megapascals. The joint efficiency, E, is 0.85. Using the same equation, T equals PR divided by SE minus 0.6 P. Substituting the values, T equals 2.5 multiplied by 1,200 divided by 138 multiplied by 0.85 minus 0.6 multiplied by 2.5. The numerator is 3,000. The denominator is 115.8. Therefore, the required thickness is 25.91 millimeters. Notice the effect of joint efficiency. When joint efficiency decreases, the effective allowable strength of the joint decreases. A greater shell thickness is therefore required to contain the same internal pressure. We will now use UG-27, paragraph C, item 1, to calculate the vessel part MAWP. For in-service calculations, An API 510 examination problem will normally provide the actual ultrasonic thickness, radius, allowable stress, and joint efficiency. The objective now becomes to determine the maximum pressure the shell can safely contain. This is called the vessel part maximum allowable working pressure. Remember that a vessel may contain several pressure-retaining components. The final vessel, MAWP, is normally controlled by the component with the lowest applicable MAWP after any required static head adjustments. Rearranging the UG-27, paragraph C, item 1 equation gives P equals S multiplied by E multiplied by T divided by R plus 0.6 T. Before calculating an in-service MAWP, the thickness must be adjusted for the corrosion expected before the next internal inspection. The projected thickness at the next inspection is usually calculated as the actual thickness minus the corrosion rate multiplied by the next internal inspection interval. For the examples in this lesson, the projected corrosion loss is already given as 2 millimeters. Therefore, T equals the actual thickness minus 2 millimeters. Here, the 2 millimeters represent the projected corrosion loss before the next internal inspection. Consider example 3, calculating vessel part MAWP. The actual ultrasonic thickness is 18 millimeters. The projected corrosion loss is 2 millimeters. The inside radius is 1,000 millimeters. The allowable stress is 138 megapascals. The joint efficiency is 1.0. Step 1. Determine the future thickness. The future thickness equals 18 minus 2, which gives 16 millimeters. Step 2. Calculate MAWP. P equals SET divided by R plus 0.6 T. Substituting the values, P equals 138 multiplied by 1.0 multiplied by 16 divided by 1,000 plus 0.6 multiplied by 16. The numerator is 2,208. The denominator is 1,009.6. Dividing gives 2.19 megapascals. Therefore, the vessel part MAWP is 2.19 megapascals. Now consider example 4, vessel part MAWP with spot radiography. The actual ultrasonic thickness is 22 millimeters. The projected corrosion loss is 2 millimeters. The inside radius is 1,200 millimeters. The allowable stress is 138 megapascals. The joint efficiency is 0.85. Step 1. Calculate the projected future thickness. The thickness equals 22 minus 2, giving 20 millimeters. Step 2. Calculate MAWP. P equals SET divided by R plus 0.6 T. Substituting the values, P equals 138 multiplied by 0.85 multiplied by 20 divided by 1,200 plus 0.6 multiplied by 20. The numerator is 2,346. The denominator is 1,212. Dividing gives 1.94 megapascals. Therefore, the vessel part MAWP is 1.94 megapascals. Here is an important examination memory tool. For required thickness, use T equals PR divided by SE minus 0.6 P. Use this equation when pressure is known and thickness is unknown. For vessel part MAWP, use P equals SET divided by R plus 0.6 T. Use this equation when thickness is known and pressure is unknown. For an API 510 in service MAWP problem, use the projected thickness available at the next inspection. This is normally the actual ultrasonic thickness minus the projected corrosion loss. This ensures that the calculated pressure is based on the thickness expected to remain before the next internal inspection. We will now examine UG-27, paragraph D, for spherical shells. The code states spherical shells. The minimum thickness or maximum allowable working pressure of a spherical shell shall be determined by equation 3. The code further states when the required thickness of a shell under internal pressure is to be calculated, the following equation shall be used. The spherical shell equation is T equals P multiplied by R divided by 2 SE minus 0.2 P. This equation is applicable provided that T does not exceed 0.356 R, or P does not exceed 0.665 SE. In the equation, T is the minimum required thickness, P is the internal pressure, R is the inside radius, S is the maximum allowable stress value, E is the joint efficiency. What is the code telling us? Just as with UG-27, paragraph C, item 1, UG-27, paragraph D can be used for two purposes. First, it can be used to calculate the required thickness. When pressure is known and thickness is unknown, calculate T. Second, it can be rearranged to calculate vessel part M, A, W, P. When thickness is known and pressure is unknown, calculate P. This is the typical API 510 in service MHRST AWP calculation. Why is the formula different from the formula for a cylindrical shell? A cylindrical shell uses T equals PR divided by SE minus 0.6 P. A spherical shell uses T equals PR divided by 2 SE minus 0.2 P. A spherical shell distributes internal pressure loading in two principal directions more uniformly than a cylindrical shell. As a result, for the same pressure, radius, allowable stress, and joint efficiency, a spherical shell generally requires less thickness than a cylindrical shell. Consider example 1. Required thickness of a spherical shell. The pressure is 2.0 megapascals. The inside radius is 1,000 millimeters. The allowable stress is 138 megapascals. The joint efficiency is 1.0. Using the spherical shell formula, T equals PR divided by 2 SE minus 0.2 P. Substituting the values, T equals 2.0 multiplied by 1,000 divided by 2 multiplied by 138 multiplied by 1.0 minus 0.2 multiplied by 2. The numerator is 2,000. The denominator is 275.6. Therefore, the required thickness is 7.26 millimeters. Now consider example 2, which uses a lower joint efficiency. The pressure is 3.0 megapascals. The inside radius is 1,200 millimeters. The allowable stress is 138 megapascals. The joint efficiency is 0.85. Substituting into the spherical shell equation, the required thickness equals 3 multiplied by 1,200 divided by 2 multiplied by 138 multiplied by 0.85 minus the 0.2 multiplied by 3. The numerator is 3,600. The denominator is 234.0. Therefore, the required thickness is 15.38 millimeters. We will now move to UG-32, paragraph C, for ellipsoidal heads. The code states ellipsoidal heads with E T sub S divided by L greater than or equal to 0.002. The required thickness of a dished head of semi-ellipsoidal form, in which half the minor axis, which is the inside depth of the head, minus the skirt, equals 1/4 of the inside diameter of the head skirt, shall be determined by the following equation. The equation is T equals P multiplied by D divided by 2, SE minus 0.2 P. What is the code describing? It is describing a 2-to-1 semi-ellipsoidal head. This means the head depth equals D divided by 4. In other words, half of the minor axis equals 1/4 of the head diameter. In practice, when an API 510 examination question states that the component is a 2-to-1 ellipsoidal head, use the UG32, paragraph C, equation. Consider example 1, calculating the required thickness of an ellipsoidal head. The pressure is 2 megapascals. The inside diameter is 2,000 millimeters. The allowable stress is 138 megapascals. The joint efficiency is 1.0. Using the equation, T equals PD divided by 2 SE minus 0.2 P. Substituting the values, T equals 2 multiplied by 2,000 divided by 2 multiplied by 138 multiplied by 1.0 minus 0.2 multiplied by 2. The numerator is 4,000. The denominator is 275.6. Therefore, the required thickness is 14.51 millimeters. Now consider example 2, calculating the MAWP of an ellipsoidal head. The actual thickness is 20 millimeters. The projected corrosion before the next inspection is 2 millimeters. First, calculate the projected thickness. The projected thickness equals 20 minus 2, giving 18 millimeters. The required thickness equation must now be rearranged to solve for pressure. The rearranged equation is P equals 2 SET divided by D plus 0.2 T. Substituting the values, P equals 2 multiplied by 138 multiplied by 1.0 multiplied by 18 divided by 2,000 plus 0.2 multiplied by 18. The numerator is 4,968. The denominator is 2,003.6. Dividing gives 2.48 megapascals. Therefore, the vessel part MAWP is 2.48 megapascals. We will now consider UG32, paragraph A, for hemispherical heads. The code states hemispherical heads. The required thickness of a hemispherical head shall be determined by the following equation. The equation is T equals P multiplied by L divided by 2 SE minus 0.2 P. In this equation, L is the inside radius of the hemispherical head. Notice that the hemispherical head equation resembles the spherical shell equation. However, the geometrical variable used for the head is L, which represents the inside radius of the hemispherical head. We must also consider the cylindrical shell formulas contained in Section 8, Division 1, Appendix 1. The Appendix 1 cylindrical shell formula is based on outside diameter and may be used in the API 510 examination. The Appendix 1 cylindrical shell approach differs from UG-27 because the UG-27 equation uses the inside radius, while the Appendix 1 equation uses the outside diameter. Therefore, before selecting an equation, always examine the dimensions given in the examination question. Check whether the problem provides the inside radius, R, or the outside diameter, OD. Do not select an equation merely because the component is cylindrical. The equation must also match the dimensional basis provided in the question. Using an outside diameter in an inside radius equation, or using an inside radius in an outside diameter equation, will produce an incorrect answer. What is not required? The API 510 examination does not require the Appendix 1 formulas for non-standard heads or special head geometries. Therefore, focus your preparation on UG-27 cylindrical shells, UG-32 ellipsoidal heads, UG-32 hemispherical heads, and the Appendix 1 cylindrical-shell formulas. Do not spend significant study time on Appendix 1 formulas for non-standard head geometries. We will now briefly discuss external pressure under UG-28. The inspector will not be required to perform external pressure calculations during the API 510 examination. However, the inspector should understand what external pressure is, where it may occur, and the type of failure it can produce. UG-28 covers shells and tubes subjected to external pressure. External pressure exists when the pressure acting on the outside surface of a vessel exceeds the pressure acting on the inside surface. This may occur when the vessel operates under vacuum, or when an external chamber or jacket applies pressure to the vessel wall. Typical examples include vacuum vessels, distillation columns operating under vacuum, condensers, drums subjected to vacuum conditions, and jackets surrounding vessels. Unlike internal pressure, where failure is normally associated with tensile membrane stress, external pressure can cause buckling, collapse, or elastic instability. A vessel may have sufficient wall thickness for internal pressure and still be vulnerable to collapse under external pressure. Resistance to external pressure depends not only on thickness, but also on vessel diameter, unsupported length, material properties, temperature, geometry, stiffening rings, and imperfections in the shell. For the examination, remember the central distinction. Internal pressure tends to stretch the shell and create tensile stress. External pressure tends to compress the shell and may create instability, buckling, or collapse. Detailed UG-28 external pressure calculations are not required for the inspector examination. That concludes Part 2 of the API 510 Exam Calculation Masterclass. In this part, we covered internal pressure calculations, required thickness, vessel part MAWP, cylindrical shells, spherical shells, ellipsoidal heads, hemispherical heads, Appendix 1 considerations, and the basic principles of external pressure. Before leaving, remember the basic examination strategy. First, identify the component geometry. Second, determine whether the question gives an inside radius, inside diameter, or outside diameter. Third, identify whether pressure or thickness is unknown. Fourth, select the correct equation. Finally, adjust the measured thickness for projected corrosion loss before calculating an in-service MAWP. Subscribe to Integrity Insight so you do not miss Part 3 of the API 510 Exam Calculation Masterclass. Part 3 will cover static head, pressure testing, and important non-calculation sections of the ASME code. Included in the API 510 body of knowledge, including impact testing, weld attachments, and nozzle reinforcement. Understanding the formulas is important, but passing the examination also requires knowing when each formula applies. Keep practicing, review the equation limits, and always read the examination question carefully. I will see you in Part 3.